Here we're going to look at ranking some acids. We've got 5 acids and we're going to arrange them by, let's go increasing strength. It just says arrange the following in order of strength as acids. Let's go weakest to strongest. Now, one of the best ways of looking at strength of an acid is by comparing Ka values. Anytime you have an equilibrium constant, equilibrium constants are always a ratio of product over reactant. So the larger the Ka, the more product. And in this case, we're talking about the tendency of these acids to dissociate to form product ions. And with acids, one of those product ions will always be hydrogen, or sometimes we say hydronium, H3O+. Strength of an acid, or base for that matter, has nothing to do with pH. It has nothing to do with the molarity or the concentration. The way that we gauge the strength of an acid is by looking at its tendency to ionize and form hydrogen. Now, that could be measured by a Ka value. The larger the Ka, the more likely it is that the acid dissociates to form hydrogen. Or sometimes we're given like a percent dissociation, where strong acids would dissociate 100%, that they fully ionize, whereas maybe a weak acid would only dissociate maybe 1%, maybe 10%. And so I do have a table here of Ka values, and so one great way of ranking these acids would be to look at increasing Ka. Now, the first particle listed is actually water. And so water doesn't really have a Ka. Water has a Kw. Whoa, that's kind of thick. Let's make that a little skinnier. So the Kw is the dissociation constant for water. Its tendency to self-ionize and form hydrogen and hydronium or hydroxide. So Kw for water, as long as we're at 25 degrees, which let's assume that we are, is always 1.0 times 10 to the negative 14th. And so water does self-ionize, and so water can dissociate to form hydrogen, or sometimes written as hydronium, and hydroxide. So we kind of said water can act like an acid or a base. It can produce the hydrogen, which increases the hydrogen concentration, obviously, or it can produce hydroxide, which could decrease the hydrogen concentration. But look at its Kw. Its tendency to dissociate is so tiny. So 99.9% of all the particles in a sample of pure water are really just neutral H2O molecules. Yeah, it self-ionizes, but not by much. So if we're going to start ranking these particles by increasing dissociation constants, water is kind of the loser. Let's go H2O. Could it act like an acid? Well, kind of. It can produce hydrogen, but not very much. Kw is 10 to the negative 14th, tiny. All right, now I have HF. That guy's kind of in the middle. HCl, I don't see on here. We'll have to deal with that guy. HNO2, there he is, and HCN. There we go. So let's say I'm going weakest acid to strongest acid. Well, then the next smallest dissociation constant would be the HCN. And if I'm looking at this chart then, the next smallest dissociation constant would be HNO2. Then just a little bit stronger would be my HF, which all seems great, except for one. I'm missing the HCl, right? It's not on this chart, and there's no Ka value listed. Aha! Often they do not list Ka values for strong acids. And so it's good just to know common strong acids would be things like HCl, HNO3 is nitric acid. H2SO4 is sulfuric acid. Things that you've kind of worked with in the past are probably strong. All of the hydrogen halides are strong except for HF. And so like if you had HCl, HBr, HI, those all ionize fully as well. They're just not that common. These might be the most common strong acids. So those I probably would remember just because they're not likely to give me a Ka. And so yeah, I just know now that HCl is a strong acid, and so it's going to fully ionize. Whereas the other three in the middle, those are weak acids. Their Ka values are all really small. They're less than 1. I mean, the Ka for HCl is like 10 to the 8th power. It's crazy large. And then, yeah, water could kind of act like an acid. It can produce hydrogen, but not very much. So it's the weakest of all those acids, I guess. Well, that wasn't so bad, right? So we're kind of thinking about increasing tendency to ionize, increasing by their Ka values. Okay, so now the second part of this says to use that table and arrange the following in order of their strength as bases. Well, that's interesting. Their strength as bases. Well, I mean, water can act like a base. It can produce hydroxide. And look at all the other ones. They're all negative ions, which normally you've been told that hydroxide is the sign of a base. And it is. It's a great base. I mean, most soluble hydroxides ionize 100% and form tons of OH hydroxide ions. But all of these negative ions can also act like bases. Here's kind of what would happen. Let's say I have fluorine ions and they're in water. Well, a negative ion is attracted to things that are positive, like hydrogen. And so this negative ion, depending on its strength as a base, could take a hydrogen off of water. You would end up with HF, but then look at what else would be produced. If I take a hydrogen away from water, I'm left with hydroxide. So often negative ions have the potential to act like a base. If we say the definition of a base is a particle that can accept hydrogen, it reacts with hydrogen, it removes hydrogen from a solution. It's just that here the hydrogen donor might be the water, and then the hydrogen acceptor would be these negative ions. That when you look at the whole equation, oh yeah, we're producing hydroxide. It's just that it's coming from the water. So this would be a solution that would qualify as a base. All right, so let's see if we wanted to rank these in order of strength as bases. There's a couple options. So one option would be that we could rank them by their Kb values. So Kb would be the tendency of the particle to accept hydrogen and remove hydrogen. And so a couple options. There is this cute little equation that we can use. It's that Kw equals Ka times Kb. And so you could actually solve for all the Kb's if you wanted to. And then the higher the Kb, the more likely it is to act like a base. And so if I wanted to really calculate a Kb, let's say I was looking at fluorine. I'd say, all right, Kw is a constant. It's in your packet. It's 1.0 times 10 to the negative 14. Ka is given to me on this table. So if I'm doing HF, let's see here. It would be 7.2 times 10 to the negative 4th. And so then, yeah, I can solve for the Kb. So the Ka, this is in reference to the HF. The Kb will be in reference to that fluorine ion, the conjugate base. And so you could plug this in your calculator and actually solve for the exact Kb value. And so I get about 1.4 times 10 to the negative 11th. You could do that. It's fine if you have a calculator, but if you don't have a calculator, then we're just going to estimate. And that's totally fine, because they'll never give me anything that I can't get right on a multiple choice question by just estimating. So let's look at some of these Kb values. Now, water's Kw will be the same whether we're thinking about water acting like an acid or acting like a base. Its tendency to dissociate is 10 to the negative 14th. It can act like an acid and produce hydrogen, or it can act like a base and produce the hydroxide. So Kw is going to be the same, 10 to the negative 14th, whether it's acting like an acid or whether it's acting like a base. Now, if I have a calculator, I can obviously do kind of what I did in blue. I could calculate the Kb's. If I don't have a calculator, I'm just going to use my noggin and estimate. So what I'm doing is like taking that 10 to the negative 14th and dividing by the Ka. Well, do you remember how like if you divide in scientific notation, you just subtract the exponents? So I'm just going to do that. I'm going to say 10 to the negative 14th, I guess like divided by 10 to the negative 4th. I'm just going to subtract the exponents. So 10 to the negative 14th would be like negative 14th minus negative 4. So I'm going to say that this is approximately a Kb of 10 to the negative maybe 10. And this was like the Kw. Now I can kind of just do that to all the other ones. Maybe not the chlorine. We'll deal with chlorine because I don't have a Ka. But I could kind of do that with these guys. Or I could say, the NO2. Well, now with this one, I'm going to have to estimate, if I'm estimating, that it's actually probably kind of close. On a free response, we could pull out our calculator and actually calculate the Kb to see which is higher or lower. In a multiple choice, they won't give me these two because they're too close. But I can show you a way to kind of figure them out. Let's say I do the same thing with the cyanide ion. I kind of estimate. So is Ka is 10 to the negative 10th. So if I had negative 14th minus negative 10th, I'm going to say the Kb is approximately like 10 to the negative 4. Okay, so I can kind of get this thing started. If we're going to start with the weakest base, well, right now it kind of looks like maybe water if I'm just looking at the Kws. Water is not a very good acid and it's not a very good base. It can act like either, but it's just not very good. Okay, so now let's see here. I've got, if I ignore chlorine, we'll figure him out later. I've got these two in the middle that both have Kb's that are really similar. They're both about 10 to the negative 10th. So without using my calculator, how can I figure out which is stronger as a base? Well, guess what? The stronger acid means that it has a higher tendency of going forward. And so the HF is just a little bit stronger as an acid, which means it's more likely to go forward and act like an acid, dissociating to form hydrogen. That means that it's less likely to go in reverse and have the fluorine act like a base. It could, but it's less likely. So for example, the dissociation equation for the HF in water would look like this. I'm going to lose the hydrogen. This guy's going to act like an acid to form the conjugate base. And then the H3O, hydronium, which is a sign of an acid. Awesome. Okay, so if this reaction has a higher tendency of going forward, it means that the acid is stronger than its conjugate base. If the conjugate base, fluorine, if that fluorine ion were a good base, then it would take the hydrogen back from the hydronium and shift it in reverse. But if you have a stronger acid, then it favors the forward a little bit more. But now if that NO2 is a little bit weaker acid, it means that its conjugate base is a little bit stronger. And if it's a weaker acid, then its equilibrium doesn't lie as far forward, which means then that the base is really good at picking up hydrogen and removing it from the solution. If the base can remove hydrogen from a solution, then that shifts it in reverse. And so here we can kind of go like opposite of the strength as acids. And so the NO2 was a little bit weaker acid, so it's got a little bit stronger conjugate base. The fluorine, the HF, was a little bit stronger acid, so his conjugate base is a little bit weaker. And then so far it looks like the strongest base would be I'll put the cyanide in there. It's got the highest Kb. Okay, so that all seems fine, but where does the chlorine go then, right? Actually, the chlorine is the loser. The chlorine is the worst base ever. And so here's the deal. If you have some of these strong acids fully ionized, so if I squeeze it in here like HCl, doesn't even usually have a double-sided arrow. It fully ionizes, it goes forward 100%. Well, that means the chlorine is a terrible base. It's an awful terrible base because the job of a base is to remove hydrogen and then shift it in reverse. And that's just never going to happen. So if you have chlorine, nitrate, sulfate, the conjugate base of a strong acid, they're terrible bases. Like that chlorine and nitrate, they're probably the worst bases ever. They're even weaker than water. Water we still write as a reversible reaction. It can form some hydrogen, just not much. That chlorine will never, ever pick up the hydrogen and shift that reaction in reverse. If it were to collide with a hydrogen, they instantly dissociate, and they'll always stay ionized in solution. So the worst base is always the conjugate base from a strong acid. And so here's my final rankings. And then this was my strength as acids.